Hello viewers, today we'll learn about second order system. The standard form of closed loop transfer function of a second order system is C of S by R of S equal to omega n square by S square plus 2 zeta omega n S plus omega n square, where omega n is nothing but undamped natural frequency in radians per second and this zeta is nothing but damping ratio. This damping ratio would tell us about nature of the oscillations being suppressed at the output end. And every practical system will be having certain damping. Now, depending upon this damping ratio, we have four types of systems. That is case 1, zeta equal to 0, that is undamped case, where the oscillations will never die out and the system will be continuously oscillating. That makes the system unstable. Now, the second case would be in between 0 and 1, that is underdamped case. Now, the next case would be zeta equal to 1, that is critically damped, where the oscillations will die out very quickly. And the last case would be zeta greater than 1 over damped case, where there will be very less oscillations at the output end. Now here, the characteristic equation of second order system is nothing but S square plus 2 zeta omega n S plus omega n square. And we are supposed to find out the roots for this quadratic equation given by the formula x square plus bx plus c equal to 0 is the quadratic equation. For this, the roots are given by minus b plus or minus square root of b square minus 4ac by 2a. And we are supposed to find out roots for this quadratic equation. Say roots s1 and s2 say equal to minus b minus 2 zeta omega ns plus or minus square root of b square is 4 zeta square omega n square minus 4ac. 4 omega n square by 2a. A is 1 here, so it is 2. Now this would be taking out the 2 common and getting cancelled. We get minus zeta omega n plus or minus omega n common here, taking it out, that would be zeta square minus 1. Now from this case 1, when zeta equal to 0, the roots will be s1, s2 will be equal to zeta is 0 and this is 0, so we do get plus or minus j omega n. Now here the roots are purely imaginary and the system is undamped, where you have continuous oscillations. Now for zeta equal to 1, replacing zeta equal to 1 here, so obviously this is all 0, then you have s1 and s2 would be equal to minus omega n. Here the roots are real and equal. The system is critically damped. That means the oscillations will die out very quickly. Now we have another case where zeta is greater than 1. We get s1 and s2 roots will be minus zeta omega n plus or minus omega n zeta square minus 1. Okay. Now here the roots are real and unequal. Here the system is overdamped. For the next case where zeta is in between 0 and 1, we have s1 and s2 as minus zeta omega n plus or minus omega n, taking out minus 1 common here, that would be 1 minus zeta square. From this, taking out minus 1 common here, that would be minus zeta omega n plus or minus j omega n root over 1 minus zeta square. This is nothing but minus zeta omega n plus or minus j omega d. This whole thing we consider this as omega d, or else omega d is equal to omega n root over 1 minus zeta square. Omega d is nothing but damped frequency of oscillation of the system in unit radians per second. So depending upon the damping ratio, we have several types of system which would tell us about the nature of the system and to what extent the oscillations are being suppressed and to what extent the system is being stable. We come to know the same information by knowing the roots also.